Hi, everyone. Welcome to our first and, God willing, our last virtual DFab demo days. This week's topic is on molecular and nanoscale digital fabrication. As Lucas and I were discussing, we believe we have a definition of digital fabrication, which is taking a high variability manufacturing process and partnering it with a programmatic interface to explore both the complexity of what you can produce as well as the variations that you can produce and run after run. I think you're going to see a lot of really interesting topics coming along here about designing at the, I guess the generous term would be the sub-micron level, kind of, as the realm that we've been discussing. Just to give you an update on things around DFab, we've been partnering with organizations on campus this week to help fight the COVID epidemic by producing over 1,000 face shields as part of this campus-wide initiative for UW Medicine. And a lot of people are continuing to work on that effort, and they deserve to be commended. And the other exciting news is DFab is an official organized research unit here at the University of Washington. So we are now officially a center. I don't know what that means other than we get to say we are officially a center, but at least we have been anointed with those holy oils. So our first talk today is going to be by Lucas Meza, who's a fellow professor in mechanical engineering, who does 3D printing at the nanoscale, working at nanomaterials and understanding both the material science when you can control things at that scale, as well as what you can program and design at that scale. So Lucas, with that, I'll turn it over to you.
Cool. All right. Do I share my screen? Can I share my screen? Yes, I think I can. If I can figure out which screen it is that I need to share. This is my presentation screen. Is that in presentation mode now?
Excellent.
Cool. All right. So thanks, Jeff. So today I'm going to be talking about some of my work on nano-architected materials. A lot of the work that we do, we heavily utilize the resources in the molecular analysis facility, which I guess will be the next talk, and then the Washington Nanofabrication facility, which is all the way down in Blue Call. And specifically, there's one tool, the Nanoscribe, that we use pretty extensively, but we also make use of all the other fun toys in there. So I am an assistant professor in mechanical engineering. This is now going into my second year. And so the first half of this will kind of be some of the work that I had done before, and then I'll talk about some of the fun projects that we've been working on here at UW. So in general, I work on nano-architected materials, and I'll walk you through what that means. But before that, I wanted to give the goal of our work. And so the bigger picture idea of what we do is engineering materials at the nanoscale. And so whenever I think about a new project, the question I'm always asking is, how do we create a new material with extreme mechanical properties? And to answer that question, we have to think back to what are mechanical properties to begin with, and what does it mean to have an extreme mechanical property? So this is an Ashby plot. You may or may not have seen one of these before, material property plot. This particular one is strength versus density. So you can see here, strength is on the y-axis, density is on the x-axis. Here we have strong, heavy stuff, ceramics, metals. In the middle, it's lighter, weaker stuff, polymers and elastomers, then foams all the way down here. And so the materials that we use, so a big part of the motivation of what we do is we want to use nanomaterials to try to help us out here. And I'm going to precurse this with, can you see my mouse too? Is that showing up? Okay, so if I just wiggle my mouse, that's like a laser pointer. So you can see here this ALD AL203 is a ceramic, but it's actually much stronger than all the other technical ceramics. It's not somewhere up here, there's diamond and carbon nanotubes and graphene. So I'm not showing the very high end of the plot, which is where this theoretical maximum comes in. But just by making things nano, we inherently enhance the properties. And so there's a whole bunch of white space here that we're looking at. This is one property of strength versus density, but there's a whole bunch of other properties, toughness, stiffness, energy dissipation, that we can look at, other metamaterial properties, thermal conductivity or electrical conductivity, dielectric constants. And so the goal of our work, what we aim to do is combine some sort of an architecture. So we make effectively 3D printed structures, but at the nanoscale. We combine some sort of an architecture that has some mechanical property to it inherently with nanomaterials. So those nanomaterials theoretically have enhanced mechanical properties for a variety of reasons. So metals, you can have a stronger, smaller effect for single crystalline metals, which is the plot you see here on the right. As you reduce the size, you get a statistical increase in strength. For ceramics, it kind of works the same way. You can get a statistical increase in the strength of a ceramic as you reduce your size. And when you start getting down to about 30 nanometers, that's where you start getting to the theoretical strength of the materials, where you're actually, the strength of the material is actually the atoms ripping apart. That's the limiting strength. There are other interesting phenomena like ductile to brittle to ductile transitions, where materials that are brittle at the macro scale actually become ductile at the nanoscale. So there's some interesting phenomena that start to take place. And all of that we try to capitalize on by combining that with architecture and intelligently designing new materials. So architecture itself, I work on nano-architected materials, but architected materials are nothing new. They've actually been around for a long time, and they are probably more common than you think. So there's different types of architected materials that we can think of, or different configurations of materials. Basically, we're combining one or two or more materials, or one material in a void, to create a new material with some new property. So stochastic architected materials like a kitchen sponge, all of you probably have sitting on your counter right now. You're using air to make something that's squishy and water absorbent. Layered materials you probably are wearing right now in your shoe. The different layers in the shoe give it some new stiffness that make it comfortable to walk. Lattice materials, cardboard, anytime you get a box from Amazon, the corrugation in the cardboard gives it some stiffness, so you can make it a lightweight box. So you take something that is wood and you make it lighter but still have some stiffness. Or fiber composites you can take with rope. You take an individual thin strand of material that has a higher strength, and you weave it into some pattern that gives it a new effective property. And so we tried to take a lot of these ideas and extend them down to the nanoscale in the work that we do. And we do that using primarily a fabrication technique known as two-photon lithography. So most of you are probably familiar with stereolithography or with SLA, DLP. Here we use, instead of UV lithography, we use infrared lithography. And the infrared light itself isn't enough to cross-link the polymer, but at the focal point of the infrared light, you can get a statistical absorption of 2 infrared photons that have the same energy as 1 UV photon, and that can actually cross-link your material only at the focal point. So you can actually get sub-wavelength resolution. So this is 780 nanometer light, and we can get features down to about 150 nanometers. So about a quarter of the wavelength of light here. And that process, we can write actually in 3D and in 2D. So you can see on the left here, this is actually the whole stage being written around in 3D. So we can make full 3D structures. We have voxel level control over structures in 3D, or we can do 2D layer by layer writing, which is generally faster, but then you lose some of the advantages of being able to trace a line around in space. So the end of that, we end up with a polymer structure. So here I'm showing off a nanolattice, but we can, in principle, make any structure we want. It's a 3D printing process. We can import an STL, the same as you would with a normal 3D printer. And to that, we then add in some post-processing steps. So a lot of the post-processing that I've focused on has been thin film coating. So you take a polymer, you coat the surface of it with some thin film. I like to use atomic layer deposition because you get very fine resolution. And then you have some coated structure. Then you expose that polymer, burn it out, and then you end up with a hollow structure. So now we have a nano-architected thin film essentially in space in any geometry that we want. So this is a kind of a lost wax method or something like that. There's other processes you can combine with these. You can change to pre-ceramic or pre-carbonic photopolymers and use pyrolysis to create a carbon or a silicon oxycarbide structure. You can use sputtering to get metals. You can do this in multiple processing steps to get different coatings of materials, different thicknesses. But I'll leave it at that. There's a whole bunch of variability in the processing techniques we have. So the end result now is we have some structure. So this is a hollow ceramic nanolattice. So you can see here the total structure is about 50 microns across, which as a reference, remember, is about the thickness of a piece of hair, depending on the person. The unit cells of these are 3 to 10 microns, and then these are hollow tubes with the wall thickness all the way down between 10 to 100 nanometers thick. And we have a control over that. So we have now a very lightweight structure that has some new mechanical property scaling depending on exactly what architecture it's in and what it's made out of. So you have the constituent property of the material and then some function of relative density for strength and stiffness, for toughness and other properties. It scales differently. So this was some of my early work. We had originally made these out of ceramics. So this is ALD alumina, so aluminum oxide, which is generally fairly strong, fairly lightweight, but it's brittle. So when we tested these out, this now, I'm going to show you a test on a 50 nanometer thick structure, which is our thick walled structure. So this is relatively thick for us. And when you test it in compression, it behaves kind of like you would expect a ceramic to. So there's a brittle catastrophic failure, no recoverability. The whole thing kind of crushes and doesn't come back. It's pretty light, it's pretty high strength, but it's not super useful as an engineering material, which say you wanted to make a lightweight airplane wing, you wouldn't want your airplane wing blowing up in the sky midway through flight. So we wanted to see if we could get around that. And we made now the same structure, same material, same geometry, just with a thin wall. So now this thin wall is 10 nanometers. And when we compress that, not only are we making use of the fact that we have an enhanced material strength, we actually start getting shell buckling. So the same thing that happens when you step on a soda can, it crumples. We can now do that with these hollow ceramic nanolattices. And we get a ductile-like behavior, not only a ductile-like behavior, but actually pretty significant recoverability. So we're now creating ductile recoverable ceramic metamaterials. And you can see that we've played with a whole bunch of different types of designs. This is a hierarchical lattice, so a lattice made of lattices. And we cyclically tested this, and you can see the recoverability is pretty repeatable. You lose a little bit of strength after the first cycle because you start opening up cracks and buckled pathways, but you still get that same repeatable deformation. So that's a fun experiment. So that was some of the work that I had done before I started here at UW. Since then, there's a few different project directions we've started to look into. Before that, so mechanical property space. So where did we actually end up with that stuff? So this is that Ashby plot. Now you see it's been extended a bit, so down to very, very low densities. The monolithic lattices, we were able to make something that was fairly strong and fairly light, that had better mechanical properties because we were making it out of a very strong ALD ceramic. And then for the hierarchical lattices, we were able to further extend that, get better mechanical properties, and actually go to ultra light weights. So here, as a frame of reference, the density of air is 1.2 kilograms per meter cubed. So that's right around here. So we were making things that were about a quarter of the density of air, which is fun. So I'm happy to talk about potential applications in vacuum balloons if anyone wants. So from that, we started, again, this was some of my past work, we started looking into new directions and what we can do to engineer better material properties. So the first area is in resilient shells. So this, I had shown, this is a zoom in of the structure before and after compression. So you can see the shell walls are wrinkled. This is an alumina shell wall being buckled. And you can see that it recovers, but then there's still cracks in the structure afterward. So that is inherently a problem, and that's why you saw that drop in the recoverability after that first cycle. So we started looking into other architectures to change the geometry of the beams themselves to fail in a certain way. And in doing that, we started looking toward origami. So origami, when you have a buckled shape, you are inherently taking on some sort of a folded structure. And absent any design, that folded structure will happen randomly, and it'll just take on the shape that it does. If you instead design a structure with a creased architecture, you can actually engineer the way that it fails. And so we've started to create these nano origami structures where these now we can coat with a thin film and compress in the same way that we did with these structures. But theoretically now, because we're engineering exactly where those creases and folds will happen, we can get enhanced recoverability. And this relies a lot on kind of the extensive wealth of origami work that people have done, which we are now just starting to scratch the surface of. There's other areas that we are looking into similarly. Here we started looking into spinodal decomposition, which actually creates structures that effectively have no nodes. This is a natural phenomenon when you combine two dissimilar materials that phase separate. They kind of spinodally decompose and form this semi-random structure. You can take that structure numerically and create a design of it, and then create a 3D printed version of that, and then coat that with a thin shell to then make a structure that doesn't have any sharp corners like the nodes here. So this has been done by a couple other groups at UC Irvine, Caltech, and we're taking that idea and seeing if we can apply it to make thermal shock resistant materials. So thermal shock being, if I take a really hot thing and I put it into a really cold bath, it'll crack. This is why you don't, you want to cool your stuff down coming out of the oven slowly, otherwise the glass will crack. So we're trying to take some fundamental principles of thermal shock resistance and density and lightweight structures, along with structural gradients, and create things that are thermal shock resistant. This one has applications in airplane turbine engines. So the coating for turbine blades in gas turbines, which normally you have a very slow ramp up so you don't crack the coating on the turbine blade. So another area, how am I doing on time?
You're kind of over.
I'm already over.
Yeah.
Oh, geez.
So if you could kind of give us like a one last takeaway and then open yourself up to questions, that would be great.
Okay. Here I'm playing with nano tensegrities. The whole world around us is full of tensegrities, both us and our skeletons and cells. We're creating tensegrities at the nanoscale using some pyrolysis to create thermally shrunk materials. Those are neat. We're also working on nano-engineered toughness to create materials with fully dense structures similar to what you see in nature, doing some micro cantilever beam testing, trying to engineer crack path deflection at the nanoscale. And all of that we're doing with this nanoscribe 2-photon additive manufacturing and a whole bunch of fun post-processing steps after the fact. So, geez, I really should have had a timer going up along with me. 10 minutes is way shorter than I'm used to. Sorry about that. So, thanks, and I'm happy to take any questions.
That's excellent. Are there any questions from the audience that you want to put into the chat and we'll read out? While they're doing it, let me ask you a question. How do students get involved in working with you at the undergraduate and master's level? This is very cool stuff.
So I have a few projects that I am always looking for students for. A lot of the work that we do, because it does rely on the WNF and the math, takes a lot of training. So I'm generally looking for students who are able to commit to longer time frames. But right now I have 3 undergrads working with me. I had 1 extra over the summer. I have a couple master's students working with me. And really it's about the project fit. So I don't think there's, I have a whole bunch of ideas for projects and directions that I want to go in. And this work is generally somewhat time consuming because we do a lot of the design from the bottom up. There's a lot of programming to create structures like this, a lot of Python or MATLAB, and then a lot of sitting in clean rooms, looking at screens and not being able to touch samples, which is a little bit different than what most people are used to. Yeah, so if there's anyone who's interested, I'm always happy to start talking about different projects. This is a 3D printing process, so it's pretty versatile, and I'm generally pretty flexible with what we work on. So feel free to reach out, but just know that I am in general a little bit pickier picking students, especially because of that long time constraint that it generally is required to make stuff.
Okay, so then we've got a question from Karl. How do you remove the core material when it's coated on the ALD alumina oxide? Isn't the ALD creating a coating without any pinholes?
Yeah, so let's see, there we go. So to cut out the structure, we use oxygen, or to burn out the polymer, we use oxygen plasma etching. So we have a plasma asher, and we use focused ion beam milling to expose the very end of that structure. So you can see for this structure, there's actually trenches on the left and right side. So we just grazed the side of the structure with a focused ion beam, which for those of you who don't know, is you shoot gallium ions at a sample and it ablates your material. So the gallium ions are heavy and you accelerate them at a high voltage. They hit your material and they blast it away, but you're doing it atom by atom effectively. So you have these little atomic cannonballs that you're milling away your sample with. And so we use that focused ion beam technique to graze the side of our sample to expose then the polymer that we then burn out using oxygen plasma.
Awesome. And then we have one last question. How do the properties of materials like two-photon lithography compare to traditional 3D printing? Are there similar flaws like voids and cracks that you produce in the process?
There are. So it depends on the writing method you're using. So I had shown you can do layer by layer or full 3D writing. So here with the 3D one, you end up with a solid polymer line that you can kind of control pretty well. In the layer by layer method, generally it ends up pretty dense, but depending on the hatching and the layering, you can create things that do have some sort of porosity. So you can see here, we're actually intentionally introducing porosity into our structure. These are the lines that are sticking out are the individual line passes from the nanoscribe, but we're doing that to mimic some of the natural gradient and porosity in tough biological materials. So you can have pores and you can have flaws the same way as a normal 3D printing process, but you have a lot more control over where those exist, which we're actually trying to use intelligently to see if we can engineer toughness.
Very cool. All right, well, thank you very much. This was a really fascinating talk. And if you have any more questions, please email Lucas. I'm sure he's happy to respond to another 10,000 emails a day. So it's a small increase in his standard workload.
But we're all just sitting at home now anyway, so.
Yeah. So next is it Micah Galls, who will be talking about the molecular analysis facility.
Yeah. Micah Glaz, actually.
Glaz, sorry.
Typo. All right, let me just share my screen. Is that in presentation mode? Doesn't look like it is. Is that in presentation mode?
Nope.
No? Okay.
Did you need me at this?
There it goes. Okay, we're good. It did, my computer wasn't responding. Okay. So my name is Micah Glaz. I am a staff scientist in the molecular analysis facility. So a little bit different than fabrication. We're on the characterization side. So after you've made your devices, you have to characterize them. You would then bring them to our lab. We have a whole host of staff scientists looking at doing surface analysis, optics, SEM, TM, X-ray analysis, etc. So we are located over in the Molecular Engineering Sciences building, which is underground on the building. So what you ever see that, if you're ever in the Molières, you see that big grass field. We're just underneath that. I apologize, I'm gonna go through these slides pretty quickly, so please bear with me. If you wanna see all of our instruments that we're gonna be talking about today, you can go to our website here. Under the instrumentation tab, you'll see a whole list of our instruments with an explanation of them and also staff contact. Our research tools kind of spans everything from nanoscale, microscale, and mesoscale, depending on, I'm just gonna move this out of my way. Depending on what you need. So for example, for high resolution, around in the nanometer resolution, we have SEM, TEM, and AFM. We have optical microscopes that can get you into the micron range and the 100 micron range. And then along with things like TOF SIMs, I'll talk about as well, which can get you into around the 1 to 10 micron range as well for imaging. Along with imaging, we also do a lot of chemical analysis and elemental analysis as well. First off, we have 2 TEMs. This is our first TEM, which can get you to 7 nanometer resolution or atomic imaging. It's really great for looking at crystal defects and grain boundaries. It does have electron diffraction on it, as well as being able to do EDS or energy dispersive. So you can do elemental analysis as well with it. which is true for most TEMs, it does require a very close attention to sample prep, since your samples do need to be less than 100 nanometers in thickness in order for the electron beam to be able to be transmitted through the sample. Our other TEM is a little bit lower resolution. However, you can do liquid imaging with this one, which is one of the really cool features of it. So it has a liquid in situ holder. You can see on the bottom right there, we have gold nanoparticles suspended in liquid that you can see there. And also we do have it does do cryo TEM as well. So you can look at cryo samples. And here we have a wound plug from a calopa plant that has been frozen, and you can image that as well. We have a suite of AFMs, atomic force microscopes. AFM is really useful for looking at topography of your samples. Unlike most electron microscopy, you do not get the topography of the sample. And so we have 3 AFMs that are really useful for that. Each of these AFMs have their own unique capability. The Bruker icon is really great for large samples. With a large sample, you can image a very large area. It does have a cooling and heating stage. You can do a lot of what's called peak force mapping, or allow you to look at the hardness or the modulus of the surface, along with liquid imaging capabilities. The Cypher, which is my favorite AFM, your sample need to be quite small, but has very high resolution and very low noise. It's great for looking at electrical characterization. So if you want to look at, say, current, or if you want to look at, usually you can look at current, you can look at Kelvin probe, which gives you the work function of your sample, etc. That is really useful techniques with the Cypher. And then on top of that, we've also now have video rate imaging. So you can actually image at a few frames per second, which is a very high rate for AFM. And so you can even watch, like, say, for example, a DNA strand wobbling around the surface, or a cell moving around the surface. You can actually image that. Last but not least is the PIFM, a photo-induced force microscope. This one is coupled with an IR laser, and it uses the AFM tip, which is about a couple of nanometers in diameter. And we can actually use that tip as a sensor. So you shine IR light on your sample. It's a tunable IR laser. And you can actually see if the sample is absorbing light or not. And it's going to give you chemical information pixel by pixel. So you can actually image a IR absorption at each pixel on your sample. With this AFM, it is also coupled with Raman. So you can do quite a bit of really neat imaging of where you get the topography and you get the chemical analysis with anywhere between 10 to 50 nanometer resolution, depending on the sample. As Lucas showed a couple of pictures of from the SEM of a nano indenter. This is one of our indenters. These are for looking at doing a type of mechanical analysis. So if you wanted to get hardness, Young's modulus, stress strain curves, etc. This is a tool you would use for that. It has liquid electrical, you can do this in both liquid and electrical chemical capabilities. It has resolution from nanonewtons, but like micronewtons. It's nanonewtons up to about 10 newtons. And it's temperature dependent as well. So you can go down to a negative 100 degrees C and up to 800 degrees Celsius. Last, the other indenter we have actually fits into the SEM. So you can image your sample while you're compressing it or indenting it. This is really useful for understanding how your material may be breaking or cracking, etc. I'm gonna keep moving forward. We're running out of time here. Time of flight secondary ion mass spec, or TOF-SIMS, is a really neat technique that gives you a molecular analysis. You actually scan a ion beam across the surface, and you look at what ions come off the surface when you do so. So that's the secondary ions. You look at those through a mass spectrometer, and so you get a mass spectrum of your sample, which is just the top 2 nanometers of the surface at every pixel. You can get between 1 and 10 microns of resolution, and you can actually etch away the surface. So you can you can actually look at depth profiling of the sample as well to look at what molecules may be further and further down in the sample. We have a whole suite of spectroscopy tools I'm not going to talk about. I just want to show them here, and since this is being recorded, you can always go back and look at this slide again, but I'm going to move forward. Finally, my last thing I want to talk about today is our suite of SEMs. We just had a brand new thermoscientific SEM as well. All these SEMs are coupled with an EDS, energy dispersive spectroscopy, so you can do elemental analysis of your samples. The nanodenser that we showed you can fit into the thermoscientific here or into the Syrian SEM over here. Finally, down below here is our FIB, focused ion beam. So while also doing SEM, you can also etch away your sample using the FIB, the focused ion beam, which can give you a little bit more analysis into your sample, as well as creating certain structures. And if you couple FIB with EDS, you can actually do cross-sectioning elemental analysis of your samples. So very quickly, I just want to show you one example. This is a nanopore ionic resistor, nanopore, sorry. This slide is courtesy of Todd Anderson and Dr. Zhang's group here at UW, where he's making these nanopores for electrochemistry. However, the way he was making them in the past, they were clogging, and so by using a very specific technique and using the FIB to create a very small 180 nanometer hole in the sample, he's able to look at, pretty much transfer a single, sorry, I lost track of my words here. It can transfer single nanoparticles through and look at the current as nanoparticles flow from through the electrochemical system, and look at the current and see how many, and get a very precise understanding of the nanoparticles by doing this. But of course, we're a characterization lab, and so although he's highly focused on the patient side, he's taking these bulbs and actually looking at them in our SEM by using the FIB to cross-section them, and then able to analyze exactly what the surface area and aspect ratio of these pores are, in order to understand exactly how this electrochemical process is happening and have a very good understanding of the nanoparticles. We have currently 5 staff scientists that are all knowledgeable in a variety of fields, from chemistry, physics, biology, etc. So we can all help in engineering. So hopefully we can not just show you, teach you how to use our instruments, but also be able to help you in with your research projects as well. If you would like to use a facility, go to our website, and there is a new user registration page right here. Click on that and get that going. And once you have that going, please feel free to send us an email to any of the staff scientists and ask for any advice or information more about the about what we have. Sorry that was so fast, but I will give it, if you have any questions, please feel free to ask.
Thank you so much. If anyone has any questions, please put them into the box. It seems like Lucas has figured out how to do the applause button. And we just wanted to, one question here from Colleen is, can you explain a little bit more about how training and access works, right? So if we're coming at this from fields that aren't traditionally nanochemical, how do we get a good enough understanding of how to even use the equipment and ask the right questions?
So usually what happens is you have a question about your sample. If it's mostly a characterization type question of, I have a contamination, or I'm making this device and we believe this elemental diffusion, etc., whatever that may be, you can come to us with pretty broad questions, and we can try to help you with it. But pretty much, you would email one of the staff scientists, and our goal would be to try to put you in the right direction. Now, we are a cost center, so if we are going to train you on one of the instruments, we do have an hourly rate for the staff scientists, and then an hourly rate for the specific instruments. No, shoot, I didn't want to do that. You can see some of our costs on this page here, but doesn't cover, it's not complete. But pretty much just come to us and ask you questions. We will train you on the instruments. Training takes anywhere between an hour to say 4 to 6 hours, depending on the instrument. Usually if it's 4 to 6 hours of training, we will put you on, we do it on a multi-day. And then we make sure that you feel confident on that instrument before we let you just use it by yourself. That answer the question?
I think it does. Thank you very much. Oh, sorry. There's one other question from Jen Menkoff, which is, what is the relationship between the MAF and the Washington Center for Nanofabrication?
Ah, that's a good question. We are both funded by the NNCI, which is a nanofabric, an NSF shared user facility, nano user facility that NNCI puts on. So we work as a team. We are our separate facilities. However, we try to work very closely together, where the WNF is doing most of the fabrication side of things, and we're doing most of the characterization side of things.
Very cool. All right, thank you so much. Next will be Zheyi Han talking about innovations in miniature lenses. I get to pronounce your name correctly. I apologize if I did not.
Yeah, it's fine. It's fine. My name is hard to pronounce anyway. Let me see where my screen. Yeah. Okay. Can you guys see my screen? Let me put it into. Is it? Are you seeing the presenter, like the slideshow? Okay. Sorry, you guys are blocking my view. Okay, good afternoon, everyone. I'm Zheyi. I'm a graduate student from the Bohringer lab of the Department of Electrical Engineering. I believe my professor is also here, and you were talking about math, and my whole project is actually fabricated in the Washington Nanofabrication facility, which you were talking about just now. So if you have any more questions about that, you can ask me. So today I will talk about our MEMS actuated metal surface Alvarez lens, which is a tunable miniature lens. So miniature lenses with tunable focus are very essential components for many modern applications involving compact optical systems in which the size and the weight of the optics are highly constrained. Conventional tunable lenses do face many challenges as miniature optical systems, such as bulky refractive optical elements, which will take up a lot of volume or has to be produced with special materials. And an interesting approach for creating a miniature lens system with tunable focus is based on Alvarez lenses, which is shown here. The left-hand side shows the typical design of an Alvarez lens system, which usually contains a pair of optical elements with complementary cubic face profile. You can see 2 pieces of them. I wonder whether you can see my mouse. Okay, so there are 2 pieces. They're separate from each other, but they have a complementary cubic face profile, and they are always overlaid on top of each other. And the optical modulation is achieved by the relative displacement between the 2 elements, which we always call half plate as well. Perpendicular, the displacement is always perpendicular to the optical axis, when you have a displacement, you are bringing in different parts of the optics in overlap, and that's how it changes the optical power of the combined system. Some researchers have integrated a pair of miniature Alvarez lens, which is in the middle, with a MEMS actuator to electrostatically displace optical elements instead of manually pulling them apart. But in their case, because the MEMS structure, you can see everything in gray. The MEMS structure are planar, while the optics are 3D. You can still see the surface shape of the optics. They have to be. That means they have to be fabricated separately, and some graduate students actually put them together manually. So that's very time-consuming and also not very ideal for mass production. Okay. So in order to reduce the 3D geometry of the lens for ultimate miniaturization of devices with high performance, metal surface optics have been developed. Metal surface optics are planar sub-wavelength structures that can control the phase, amplitude, or polarization of the incident light, and can hence mimic complex geometric curvatures on a flat, usually wavelength scale, which means couple micron thick surface. And in this case, we can convert the 3D alvarez optics elements, which is shown before, into a pair of 2D metasurface optics. So Lucas was talking about his 3D mecha material. So you can think metasurface as a 2D material in which the thickness of the material is very negligible. So crush 3D material down, we have 2D metasurface. And in this case, we are designing a pair of 2D alvarez metasurfaces with complementary cubic face surface profile. And you can see in the graph here, the top two rows are showing the pair of alvarez lens and the inverse alvarez lens. And when they are combined, which means when they're overlaid on top of each other, they form a quadratic face profile as shown below, which mimics the behavior of a conventional conversion lens. And the optical power of the combined alvarez lens in this case is modulated again by changing the center to center. You can see the center to center offset between the two face plates, and it gives a different optical power in the final conversion lens. And as shown in the plot below, if you have a larger center to center displacement between the two half plates, you will have a shorter focal length. It's somewhat a reciprocal relationship. And in our design, we chose operating wavelength to be 1550 in the IR range. And we choose the cylindrical silicon nitride nanopost on top of silicon substrate as the fundamental scattering element. And the metasurface itself is a 2D array of scattering elements. Like this is a very small image of it. Usually you have hundreds, thousands, or even millions of pillars in one metasurface. And the calculated alvarez face profile here is then mapped to 6 diameters of the nanopost to span the phase from 0 to 2 pi, while still maintaining a transmission amplitude around 1. So most of light is transmitted, but just with your phase being added. So in order to create a lateral displacement between the two alvarez metasurface, we have implemented a miniature MEMS actuator to electrostatically displace one of the metasurface relative to the other. So a typical design of a comb drive actuator consists of 2 combs structured with interdigitated fingers, of which one side is usually fixed, while the other is connected to a compliant suspension. A voltage applied across the 2 comb actuator the 2 comb structure will lead to a deflection of the mobile comb drawn towards the fixed comb by the electrostatic force generated in between the fingers. And because there is no DC current flowing in the device, nothing is touching, there is this device, the comb drive structure is very famous for produce high precision actuation with very low power consumption because no DC current. And the electrostatic force arrives from the capacitive interaction between the comb fingers, has a quadratic dependence on the voltage input. And because we're using a hook compliant structure, we have a linear relationship between the actuator displacement and the electrostatic force. Hence, the displacement is quadratically dependent on the voltage as well. So showing a potential for high controllability. And for the compliant suspension structure, we need to design to displace the actuator along x direction, which shows the folder flexure. This is called folder flexure structure, giving a very high stiffness ratio between the undesirable direction, which is y, and the desirable direction which is x. So giving us a very stable, a very mechanically stable structure for uniaxial displacement along the x direction. And the devices in our project are all fabricated in the Washington Nanofabrication facility right on campus. And for a full alvarez system, the metasurfaces were fabricated on 2 separate wafers because there are 2 of the metasurfaces. Both of them are patterned with stepper lithography for very high throughput, high precision, but low cost. And one metasurface is fabricated on the SOI wafer. The electrostatic MEMS this is the metasurface. The electrostatic MEMS platform was patterned in the silicon layer right underneath. And we use backside etching to open up the window for the metasurface optics. And then we use the HF release edge to remove the oxide. So the whole metasurface structure is in suspension, holding by some spring structure, which is not shown in this image. And the second metal surface is fabricated on a stationary wafer. And these two metal surfaces has complementary cubic surface profile. And in the final structure, they were overlaid on top of each other. And because one of metal surfaces can be actuated from left to right, we are introducing a center-to-center displacement between them. Next one. And here are the SEM images of the fabricated Alvarez device. You're actually seeing the mobile metal surface because the stationary one is right underneath because they're aligned with each other, so you can't see the other one. So this is the most important and interesting one. And you can see the metal surface. This is one of the metal surface on the center platform. And we have comb drives on the side. This is zooming, and you can see the metal surface pillars, like the quasi-periodic arrays on the metal surface to introduce different phase profile. And note that we have comb drive on both left and right. That means depends on which side we're applying the voltage, you can pull the structure to the left or to the right. So before fabricating a full Alvarez system, we wanted to verify the reliability of the MEMS platform in tuning because that controls solely controls the center-to-center offset between the two plates and hence the tuning optical power. So to do that, instead of fabricating the Alvarez structure, we fabricate the same MEMS actuator, but this time we only carry one single metal surface length. So this is one metal surface length on its own instead of Alvarez structure that need two of them. So this is one single metal surface length, giving a focal spot at the center about 200 microns away from the plate. And this whole structure is designed to be pulled along the x direction, either to left or to right. I can't make it move. Well, anyway, so this is actually a video, but it's not moving here. So the center is the focal spot, and when we apply voltage on the left side, the whole device actually pulled towards the left. And you can see the center of the focus moving towards left and then relax when you remove the voltage. And in this case, we tracked the position of the focal spot, which corresponds to the position of the center plate, the central platform. And we plotted the position, the displacement of central platform, and as well as the square of the voltage input over time. So you can see from the graph, the displacement, the trend of displacement follows the trend of the voltage square very closely, which proves the quadratic relationship we were talking about earlier, which gives a very high controllability. All the steps here are actually from the resolution limit of the IR camera, so it's not actually in the displacement themselves. But if you look at the graph in general, you can see this is a ramp up in voltage and ramp down in voltage. And you see it's very symmetric on the left and right. That means there's no hysteresis effect in this whole device, and everything is response immediately. And once we verify the platform, then instead of the single metal surface length, we now put the Alvarez plate on top of it. You are seeing the top Alvarez plate, and there's another one right underneath. And when they're overlaying on top of each other like this, we can find a focal spot about, again, 200 microns away from it. This is the focal plane. We're looking at the focal spot. And in this case, when we apply voltage, again, on the left side, this platform, the top metal surface is pulled towards left. So we are increasing the center-to-center gap between the two metal surfaces. And this moves the focal spot away from the device. So that's how, when we introduce a displacement along X, we have a focal spot position change along Z. That's how Alvarez works. And we fabricate them with the help of metal surface.
This is great. Are you ready to start taking some questions?
Yes, just this is just a graph. This is the final slide actually. So it's just, oh my God, this is such a long time. So this is just what we mentioned, like we track the focal spot along the Z direction and as a function of the voltage input and also as a function of actual displacement in Z. So you can see we are tuning about 68 micron with only 6.3 micron displacement. So it's more than 10 times tuning. So this is the last slide. And yeah, just in summary, we use nanofabrication to fabricate tunable miniature lens. And this is a joint project. So the metal surface lens is actually, the lens itself is designed by the Professor Majana's group in electrical engineering as well, and everything's fabricating, which is a nanofabrication facility. By the way, my professor is here, Professor Bohringer is here. He's the boss of the director there, so if you have more questions, it's a good time. Okay, questions?
Very cool. Thank you so much. Again, if you have questions, please type them into the group chat and I'll read them out. I guess my first question is there a limitation in terms of how much displacement you can get in your system, right? That seems like that would be a key limiting factor in terms of your accessible focal range, how far you can move the lenses relative to each other. Or is that something that you can cover quite well?
So the thing is, with Alvarez principle, the mechanism we're using, there's actually no limit on how far it can go. So actually in this case, it all depends on how good you can design the main structure. For example, in this device, this is the first round of the experiment. So we actually designed about a range, the moving range here between the fingers are 10 micron. So to safely control the device, we can only move up to 7 micron here. But we are doing more further device as well. And if you want to have more tuning range, you actually just increase the gap here. It does not change the voltage input much. That's why cone dryers are very effective in terms of displacement, micro positioning, those kind of stuff. It's basically just increase the gap here. Maybe when you go to larger range, like hundreds of microns, you need to boost up the voltage a little bit, but the whole principle can be scaled up quite easily.
Okay, if there are no more questions from the audience, I'd like to thank our speaker again. This is very interesting. I look forward to seeing these in my even new slimmer phone in the future with its dynamic focal range. And so our last speaker is going to be Al Nelson, whose work is on designing chemicals for 3D printing, beyond 3D printing actually, 4D printing.
Yeah, thanks. Jeff and Colleen, thank you very much for organizing this event. I think we've had very few occasions to be able to connect with the UW community, so it's really nice to see some faces and hear some voices again.
All credit goes to Colleen.
Yeah, great job, Colleen. And so I guess, am I in presentation mode? It doesn't seem like it on my, there we go. Okay, so yeah, what I'm going to talk about today is not so much 3D printing to create nanostructures. We saw some beautiful nanofabricated images from earlier talks and using the MAF facilities to produce them. What we're doing is actually using molecules that self-assemble into nanostructures and then using that for 3D printing. And in fact, all of the images that I'm going to show today were captured on cell phone cameras. So our motivation here for the work that I'm going to talk about really comes from the sort of actuation or movement that we see in nature. And just giving one example here of a plant, right? And so the difference here between a wilted plant and a healthy plant is water. And in fact, what's interesting is that plants are able to move, but they have no motor proteins. All of the movement that we see in a plant is entirely driven by the flow of water or the introduction of turgor pressure, where you're inflating the cells with water and then they apply pressure against the cell walls. But there are also more complex movements as well that are observed in plants, and showing two videos here, the one on the left being a mimosa plant, the one on the right being a Venus flytrap. And what we find really fascinating about these examples is that these are mechanically stimulated. So you touch these plants, and then that causes a change in shape. And so with that as inspiration, what I'll talk about today is how we're using 3D printing to program objects now that can respond to mechanical cues. And this is the work of visiting German master's student Max, and then also two graduate students in the lab, Jen and Amrita. Just to kind of get right into it, the polymer that I'm going to talk about today is one that we use quite a bit in the lab. We start from a commercially available polymer that's shown on the left. This is F127. It's a linear polymer, and then we do a one-step chemical transformation that transforms that into what we like to call F127 BUM or F127 BUM. What's important here is that we've now introduced these end groups onto the polymer that allows us to cross-link the material. And so if we take this polymer and dissolve it in water at anywhere between 25 and 35 weight percent, so that's having between 65 and 75% water, we get this hydrogel. Right? And so this vial here shows one of our hydrogels. This is an inverted vial. This hydrogel suspended at the top. There's a magnet that's supported in that hydrogel that you can see as well. And so the reason why this happens is because we have, as shown in this cartoon, and that's because we have these linear polymers that have these blue segments that are water soluble, this red segment in the middle that's not, or has some variable water solubility. And so what happens is that these polymers will self-assemble in water to form these micelles. They're about 14 nanometers in diameter or so. And then these micelles will pack and interact with each other. And when that happens, then we create this gel in water. And so we're effectively using these nanostructures then as viscosity modifiers to create gels that we can print with. So in general, the strategy in my group, in our lab, is to use stimuli responsive behaviors and materials to enable 3D printing. And that's also the case for this hydrogel that I've just shown. So we can, these hydrogels are shear thinning. So that allows us to extrude these materials from a nozzle using either a mechanical piston or a pneumatic system. Essentially what we have is a gel in the syringe, and as we apply pressure, this gel will flow out of the nozzle. But once it exits the nozzle, it doesn't feel that pressure anymore, and so it stops flowing, so we regain that gel state again. And so this allows us to create multi-layered constructs of different gels. And then after we've printed the entire construct, what we do is we do a photocure where we shine it with UV light, induce a photopolymerization of those end groups that we introduce onto the polymer, and then we get these robust elastomeric materials. Right? So they're still hydrogels. But we can hold them with tweezers, you can squeeze them a bit, and they're pretty sturdy. Now, one limitation of using a hydrogel is shown in what I would describe as Jen stuck at home doing this demo for us. And so what she's done is to produce this hydrogel, which is Jello, and she created it in a mold. But of course, if you leave Jello out over time, what happens is that water will evaporate, right? So Jello, just like all other hydrogels, is mostly water. And water can evaporate from this system, and you're left behind with this dried construct. But when you have this dried construct, then it doesn't have the same type of material properties as what you started with. And so for that reason, what my group has done is to replace water as a solvent with other high boiling solvents or solvents that have a low vapor pressure. And this is where we've turned to ionic liquids. And I show the structure of 3 different ionic liquids on this slide. But if we go to this cartoon on the lower left here, it kind of shows you what's going on in this system. And that we still form these micelles in solution, but now the solution is not water, the solution is an ionic liquid. And so in one case, if this is the structure of the ionic liquid represented by these black dots, this is the form of the gel that we can now print with. But then after we've printed our construct, we shine it with UV light, and then what we can do is actually polymerize the solvent. So all 3 of these ionic liquids that we have shown here have a vinyl group on them. These vinyl groups can undergo radical polymerization. And so when we polymerize the solvent, we now introduce this polymer network where these micelles are trapped within. Now, another important, an important difference, I should say, between these 3 ionic liquids that I have shown is the length of this group here. So here I have a 2-carbon side chain. Now here's a 4-carbon side chain, and then finally a 6-carbon side chain. And the reason why this is important is because this starts to alter the mechanical properties of the materials that we print. So whereas when this side chain is short, we get a more tough, hard material. As we increase the length of this side chain, then we get more elastomeric properties. And so the side chains can affect the stiffness of these materials, probably easiest to show in the form of these videos here. So when that chain is short, we call this ethyl, then the material is more stiff, versus butyl, there's a little bit more flexibility there, versus hexyl, where it becomes even more rubbery, okay? So with these different mechanical properties in hand, what we have are different inks that we can print with in a multi-material fashion. And so here's where we've start to get into something I think is pretty exciting now in introducing mechano-activated shape change. And the way this works in the simplest case is we have a bilayer that we've printed. And the bottom layer here is the butyl derivative. So this is a material that's more elastomeric, right? It shows elastic recovery versus this orange layer that's printed on top, which shows a plastic deformation, right? So the orange layer is plastically or deformed, so it permanently deforms, versus the green layer, which shows recovery. So if you take this bilayer construct, you stretch it and you let it go, what happens is that structure will now bend. And so there are ways to then create more sophisticated bending structures using this approach. And this is something that we've done with our collaborator at UCSD, Nick Beckler. And so if I gave you these two structures and I told you that we printed them, you probably couldn't tell what shapes they would produce upon mechano activation. But if you take each of these, you stretch them and you let them go, then the structure on the left will form a U, the structure on the right will form a W. Okay? And so the cartoons here show the cross sections. And again, the orange regions undergo plastic deformation. The green regions will have elastic recovery. And so, in fact, the location of the green regions relative to the orange can control the direction of the shape changing. Now, the extent of shape change does depend on how hard you pull. Right, so these are two different bilayer examples here, but in both cases, if you pull it a little bit, then it bends a little bit. If you pull it a lot, then it will bend a lot more. And so if I were to give you these two structures, and I said, well, if you pull on it and you let it go, it will change shape, then you might ask, well, how hard should I pull on these structures, right? And how will I know when to stop? And so there, we actually turned to using a different type of mechanoactivation, and this is using mechanochemistry. And we're doing this in collaboration with a former colleague from UW, now at University of Wisconsin, Professor A.J. Boydson. And so he's interested in this molecule known as spiropyran. Now, spiropyran is a molecule that can be mechanically activated to undergo an isomerization. And when you pull on spiropyran, you can rearrange some of the bonds to form this open form. And when you do, it has a purple color. So what we've done is to introduce this molecule into our formulations. And so I'll skip some of the details here, but what's important is that the color change can be introduced depending on the amount of strain as well. So now we can provide the user with information about how hard to pull, right? It's a visual cue so that you can pull a structure, and then when you see that purple color, you know that you've pulled it enough, you can let it go, and then that object will create the shape that's desired. And so, so just briefly, what I've shown then is that we have these polymers that will self-assemble on the nanoscale to create these architectures in ionic liquids, which enables these gels, and that we can print these gels. And we're really interested in this idea of using multi-material printing now to control how these gels can be used to create objects that can change shape upon mechanoactivation. And so the next big thing for us is really to look toward mechanoactivated origami. And And Lucas kind of mentioned origami during his talk as well. But the idea that you can start with some flat object and you can pull on it, and then it will turn into a glider or a box or shipping container is the sort of things that we're after now. And so, of course, just wanted to thank the people who were involved in getting some of these projects going, and I'm happy to take any questions that folks might have.
That's really exciting work. Again, if you have questions, please type them into the chat box and I'll read them out. I guess my first question is, how would production of this scale up beyond 3D printing, right? So 3D printing is generally the second best way of making anything.
Mm-hmm.
So would it be possible to do these types of processes if we have a design in a non-3D printed fashion?
Yeah, no, absolutely, absolutely. Yeah, especially thinking about larger forms of these things, it would take way too long. But these types of gels are great for casting too. So you can cast films with these. They'll the shear thinning effect, I think, is actually helpful for that. But you can use them in injectable forms as well.
Okay, would that make it difficult to do UV curing, or would you want to swap out the curing mechanism?
Yeah, so generally yes, UV curing, but we can also switch this to something that's thermally cured as well. And so yeah, we wouldn't be bound to just using light to cure the materials.
Okay, we've got a couple questions from Jen. Besides saying very, very, very cool. Sorry, I had one extra very for myself.
Yeah.
Is there the possibility of a bistable material where you can return it to the original shape? So can you pull it, it transforms, and then do something to it and have it return to its original state?
Yeah. So that's something that we're looking at now. It's possible that these can be thermally recovered, because these do resemble thermoplastics. We haven't been able to consistently get that thermal recovery. And then we're also looking at options where we might introduce a second stimuli responsive behavior that might help facilitate that recovery. So maybe using a different wavelength of light that might help their recovery.
Okay.
Yeah, I think that's a really neat idea too.
Are these safe to touch the skin? So could you put them on and wear them all day? Like what's that toy? The one that you slip onto your wrist and you slap.
Yeah, like those slapsticks. Yeah, right. I always in our labs, I always tell my students that they should wear gloves. There are other ionic liquids that are, I think supposed to be more biocompatible. There are I'm not aware of any toxic effects with these ionic liquids, but I'm always just on the cautious side. Okay. But we are also looking for other solvents like glycerol or other non-aqueous solvents that are maybe more common that could be used in a system like this too.
Okay. And then are there any other chemicals that have properties similar to spiroprene? I believe I'm saying that correct.
Yeah, so I assume can undergo maybe a color change in response to a mechanical force. Yes. So there's like a whole slew of them, and that's been an emerging field over the last, I'd say, 5 to 10 years. So if you're interested in other specific examples, I'm happy to point you to references depending on what you're looking for. So there are molecules that will undergo a color change when you mechanically activate them. And then there are also molecules that will introduce more cross-linking so that you can actually stiffen the system.
Okay. We've got a question here from Lucas, which is, are there ways to obtain different properties using a single material, i.e. grayscale photopolymer?
Oh, interesting. Yes. Yeah, so I guess if we can control the grayscale with light, then yeah, I think it'd be possible to make gradients too. Yeah, I'd have to think that through some more about how ways that we might introduce the gradient. But yeah, if we can do it with light, yes.
Very cool.
Yeah.
All right, I'll give one last second for anyone to put in their last question. But I guess the main thing is, what have been the big barriers you find in terms of defining material as printable, right? So there are a whole host of chemistries, but getting something from chemistry to something you can actually reliably print with can often be very challenging. What are your methods for kind of jumping that barrier?
Yeah, so I think along those lines, it would be awesome to have higher throughput screening methods for materials, right? Right now, we do a lot with just experience and gut feel. We generally like shear thinning materials because we think it works well for making multi-layered constructs. But some materials have a yielding behavior that's more appropriate than others, and we just haven't. We would love to have values, actual quantitative values that can would tell us like, yes, if you have these numbers, if you can show these numbers, then it will absolutely work. But we don't have that yet.
Okay. All right, seeing no other questions, thank you so much. This is really cool. Thank you everyone for coming to our first and God willing last virtual DFab. But if it's not our last one, there'll be another one in a month or so. And I hope everyone stays safe and healthy, and we'll see you in the future.
All right, great. Thank you very much.
Thank you, everyone.